Yep. Haha. Be self-conscious. All right.
Yes.
So everyone here was at the last one. Lizzie, did you get a chance to watch the last one? Cool. Sweet. Okay, so just a basic.
People.
Oh, look at that. Oh man, look how many people are chiming in. Okay, so basic review of what we talked about last time. I'm going to share my screen. This one. All right. Basic review of the stuff we talked about. Talked about modeling. We talked about different features to create. We talked about different methods of modeling, like parametric modeling, like we're used to, where we're punching in parameters and numbers for specific lengths of stuff. We talked about direct modeling, where you can do stuff like this. Where are you? Oh, there it is. Where you can literally just drag faces and do random stuff, which is always fun. And we mentioned that form modeling exists, and it's really cool. And I want to learn more about it because I'm a total dweeb when it comes to organic modeling. We learned about those.
Nice.
We learned about them in very loose terms. But last time we kind of left off with an invitation to look back at Fusion's tutorials and figure out what else you can learn from them. I'll start with what I learned. There were two really cool tricks that I thought were nifty, and I'll just show them off on this part. So one is editing faces directly. So I learned last time we had the thought of what's the difference between modeling with no design history and modeling with a design history. And I had thought that no design history meant you were direct modeling and design history meant you were parametric modeling, but I'm wrong. You can do parametric or direct editing in either one of them. As far as I know, there's no reason to not turn on the timeline. So if anyone finds a reason, let me know. But I'll show you can direct edit in here. And one of the cool things that I learned that Fusion people do all the time is they use this press pull function, and they use the move tool a lot. So when you select faces and use the move tool, it opens up right here. You get your move copy box, and there's this free move button, which does a lot of weird things. Wow, I don't know how that even happened. The free move does weird stuff, but if you come into translate or rotate directly, it'll remember exactly what you did. So I can rotate about that axis, put a draft on that face. I can come in and I can, no, where's press pull? I can come in and I can press pull both of these corners, put a radius on that. And then, interesting thing I learned too, so you can extrude a face directly, and that does about what we'd expect. It takes that face and it extrudes it directly out. I was confused about where press pull differs. If I try to press pull this, it'll bring those fillets with it, and it'll try to preserve the geometry as it exists. So press pull is one that's interesting to work with, and move copy is one that's interesting to work with. I'll show you all one more trick too that they talked about that's really useful with pulling in imported geometries. I don't have anything that's broken here, but let's say this corner right here was super mega broke. And we've got like an orgy of fillets right here. And we've just got some weird features right here, and we can't edit. Like, let's say we want to pull this face back for some reason, or just whatever we want to do. And I try to pull that back and everything breaks. There's a method you can use called the wound heal method. So basically what you want to do is you want to take your part and you want to break it, and then you want to fix it. So I come in and I create a sphere, and I want to do it on that face at that point. And I just come in and I make a sphere that engulfs whatever geometry I don't like. I wound it by creating that, and then I just go back in and I delete that sphere, and everything goes away. Wow, that was wonderful. Yeah, let's not do a sphere that big then. Well, when they did it, it wasn't as bad. But basically what you can do is you can, come on, let me select my point again. Yeah. Sorry guys, I thought this was gonna be cooler than it was. But basically the concept is you take a sphere and you bust up your model and then you fix it by deleting that face. And usually Fusion can recover geometry and it can make edges square again when there's a bunch of weird fillets intersecting, and you can go in and put normal fillets on them. If you want to learn more about that, watch the direct editing one. But it seems like a pretty useful thing when people bring in broken geometries or something that's just janky and you don't want to have to sit there while they go fix their part for 20 minutes. Okay, those are the main things I learned. Oh, one more. This is really cool too. So let's say I'm extruding something. Fusion gives us a really cool option when I drop down here. So if I'm extruding this face, I can punch in a number that I want it to extrude out. Or I can come in and I can re-anchor and say, actually, I want to measure that extrude from this face. So then the number that I'm punching in is an offset from that face as opposed to a distance. So it saves you a little bit of measuring. Like I want to make that gap minus 0.2 inches. Perfect. Now I have a slot that's 0.2 inches wide right there. And once again, that was in press pull or in anytime you're punching in a distance, you can re-anchor where that distance is measured from. Okay, those are my biggest things I learned. Any questions about them first off? Okay, great. Did anyone else learn anything that they think is particularly cool and they want to, you can just explain it if you want to, or you can show it off if you want to as well.
Quick comment, Tyler.
Yeah.
Everything that Tyler just went over with direct modeling applies in Mastercam's direct modeling as well, up to the wound heal. That obviously Mastercam doesn't do that. It's super cool. But all those concepts are the same in Mastercam for those who use Mastercam.
Oh, one other concept that I forgot to mention is if you're ever, share screen again. If you're ever working on something, oh, there you go. If you're ever working on something weird, and let's say you want to try one of those direct editing methods and work with some funky faces, what they recommend doing is they recommend splitting your geometry. So I come in and I make a plane or something. I want to mess with this corner. I make a plane right there, and I come in and I split my body. So split that body along, where's my, hiding, splitting tools, with this plane right here. So I can come in and I can split that, and then I can hide this body. And then when I'm working with things, a lot of times those wound heal methods will work better on a smaller chunk, and then you show that body again and you just combine them. So the suggestion was cut off the chunk that you want to work on so Fusion doesn't have to recompute all of the faces over your entire body and then remerge it back in. But I think that's a tool that applies to Mastercam and any other like editing as well. You can cut a chunk off, work on it, reattach it, and move on with your life. Okay, what else did you guys learn that you thought would be interesting to share?
I was messing with the rule number 1 because it's just like it says add new component, and I was like, I don't know what that is. I want to do sub-assemblies and stuff like that. So I finally found out how to do, like how to organize my tree because it got real messy. Like some 300 parts, and I'm like, I can't read anything. So finally figured out that a component can also be a sub-assembly, and that was cool.
Nice. And for those of you who weren't here last week, that rule number 1 is basically as soon as you make an object, you should come in. You should come in and you should create a new component from that body. And then anything you do to this will then have its history in the main thing. But if you come in and activate that component, that will also exist under that specific component. So you can activate any individual component and see exactly what's been done to that here. If you're just editing bodies, you won't keep a history by body. You'll keep a history as a total. I wasn't sharing my screen, was I?
No.
No. All right. That's okay. Here, let me show you what I was talking about.
Parts in other projects if you need to.
What was that?
You also do it so you can reuse parts in other projects or in other pieces. Or like if you want to duplicate a piece and then or create another instance of it, when you edit it, you'll get those same edits on the other instance. So it'll affect both at the same time.
Awesome, Corbin. Good job. Okay. Anyone else have anything revelatory they want to share?
It's not super relevant, but apparently Fusion 360 has some like slicing capabilities for additive manufacturing.
They're weird, but they exist. If you want to take a look at them, Corbin, and let us know how well they work. I'm curious. I just don't know what Fusion would even do to make a slicer work better than what exists. But if you find anything cool, let us know.
I think that you just don't
one
have
of the main benefits of having the slicer in Fusion is you don't have to like re-export STLs or anything.
Yeah, good point.
We'll reslice it just right there.
And you're cloud-based.
Good point.
Big problem is that to generate that slice, it takes like 2 minutes. It's ridiculously long because it has to generate it in the cloud.
And then beam it back to you. Interesting. Cool. Well, let's start looking at VMC tooling. Did anyone get a chance to look at that Fusion 360 lesson that we put up? Okay. Well then,
making the tool.
Yeah. So fundamentals of milling lesson 1 was tool library. Okay, so who wants to give a 1-minute recap on what a tool library is and how we use it?
I can try.
All right, go for it.
Okay, so you have like the tools that you physically have. Let's say the tools we physically have in the shop. You have the dimensions and what kind of material, what's holding it, all in that list. And then you can call on that list when you're camming, so then the right tool is used at the right time. So then the machine can follow that, call that tool, and use it.
Nice. Perfect, Lizzie. Any addendums to that? I'll add one. A tool library is also, it does as much, I'll add a caveat to it, I guess. A tool library does as much as you're wanting to put in effort. So in Mastercam and in our Fusion library, so right now I have pulled open our DM1 library and our VF4 library that we have in Fusion. Those I'll share with you guys. They're created by Alex Laraway, and they're out of date, so we need to update them. But they only do as much for you as you're willing to do. So when I come in and I look at this, I see it's our 3/8 inch end mill, and it's in a tool holder that looks like this. I think he has it. I think that's an ER call it, or a TG call it. I can check for collisions if I have this stick out here measured right, and the diameter of this thing right, and all of this information correct. But we have, I don't know how many of us touch the CNCs, but we're all scooting tools in and out. We're changing tool holders. We're doing all sorts of weird stuff to the machine. One of the downsides of believing too much in your tool library's information is it might be wrong. I might have come in and I might have taken this tool and scooted it a little bit into the collet. So you think you're going to have 50 thou clearance, but you actually don't, and you can crash the part if you just trust that.
How dare you?
Austin, so it's been a while since I've been there, and I know we just updated everything. Did we do anything with Mastercam's libraries to update tool holders and stuff?
There are still some parts that are out of date. So all the tools are correct.
Cool.
Never trust stickouts. I second what Tyler says. They
Yeah.
change job to job. Mastercam actually does it interesting. The stickout is determined by your operation. It's not inherent in the tool library. So they assume that it's going to be operation specific. So you can put that in your operation.
Cool.
But yeah, don't trust stickouts. The tool holders are all there. Currently, a couple of them are not in the correct tool holders, but we have the geometry for every holder we use.
Cool.
I have a quick question.
Yeah, punch it.
So in the video, it talked about, and I can see here, like you have like the different libraries, like you have the cloud, the documents, local, vendors, and samples. I'm assuming that the vendors and samples are completely irrelevant for us. Is that correct? Just because like we're not using their tool libraries, or do they have a use?
So that is a fantastic question. So this goes for both Fusion and Mastercam. You end up using the samples a lot. So you see in our DM1 standard library, tools 1 through 4 are missing, and tools 16 through 18 are missing as well. Same goes with the VF4. That's because we don't know exactly what drill bits that we're going to put in there or what other tools we're going to put later on. So that's where these samples come in handy. We don't have everything we have in the shop in this tool library. Let's say I'm putting in a drill bit. This is one thing that's different for Fusion than for Mastercam. I come into my samples and I say, okay, I want an inch drill bit and I want it in aluminum. I click on here, I find the drill bit that I want, 9/64, and then I pop that into my tool library and it comes with some information that I then want to edit and make sure it corresponds with the tool that we have. So in short, Benjamin, yeah, you use these samples all the time. The vendors, these are mostly tool holders. So we use those when we set up our tool libraries, but that's about it. We never really change these, if that makes sense. If we were like a professional job shop and we were going to do like 3,000 of an individual part, we would get everything dang right before we even start a part. So that way we could just say, okay, trust it and go. But everything we do is one-off, so it's not worth it. Good question, Benjamin. Yeah.
Another question real quick.
Yeah.
Is it possible to put the DM1 and VF4 libraries onto the local?
Yes. So is everyone, who is not familiar with cloud versus local? Is there anyone in this group not familiar with the cloud versus local? Brief recap is everything cloud-based is stored on my account. So in the prototyping lab, that's really nice. We can store those on the cloud and have them on every computer. Local would be a local copy of those things. If we update the cloud version, it does not update the local version. So Luke, we can put in local libraries if we want to. What would be the use case of those?
Sorry, the reason I say that is because like, if we were gonna have people doing lots of camming and stuff on these computers in the shop, that might be a useful feature, just so that, you know, if you use the computers here, everybody can have access to the same libraries. I don't know. It's something to think about.
I think that's a good discussion to have further offline.
Yeah. Good point. I will tell you guys one thing, is when you pull a tool from your tool library, like let's say I'm coming in here, I'm going to do 2D adaptive. I'm going to do, oh, this is gross. That's nasty. I come in to select my tool, and I want to pull it from the router bin. I select that 1/4 inch ball and I click OK. When I go to edit that tool, I am not in my cloud library anymore. There's a specific tool library associated with this cam that I'm doing right now. If I come in and I edit this tool and I go, ooh, I want to actually make that a 3 flute because I forgot I have a 3 flute ball and I want to use that instead. that does not update my cloud library. That edit only exists in this local library, if that makes sense.
So if you change it in your cloud, does it edit it in the document or the project that you're working on?
Yeah, let's find out. So I'll come in to my tool library. The answer is I don't know. So this is my 1/4 inch ball wood 3. Let's edit that and see what happens. We're gonna make it 0.74 inch flute length. And let's see. So then when I come in to my tool library for bleh, looks like it does not update. I'm sure there's somewhere where you can click a button and say sync my tools with the way they are in the cloud. I'm sure there's something like that, but that scares me. Having anything that edits what's going on in your cam for you is scary sometimes. Great questions, guys. Okay, any other questions about Fusion's tool libraries specifically? Okay, so you guys are aware, the way we're gonna run it probably with the new CNC router is we're going to have some libraries that we create that we hand to students. And we're gonna say, okay, these are the 10 tools, or these are the 8 tools that are loaded in the Shop Saver right now, and here are feeds and speeds with them. So you'll notice when I come in to edit this tool, feeds and speeds are part of this. And we'll be able to control how much, like what speeds people are going at. We can punch in conservative values and we can kind of set up a plug and chug thing. It's a lot more friendly in the router space than it is in the VMC space. And we'll get back to that later. Okay, so briefly we want to talk about tools real quick and the geometries of VMC end mills. We're just going to get on the same page so that we all know what we're talking about. So the number of flutes on an end mill is the number of cutting edges. Whether it's straight or whether it's spiral, they're still called flutes, cutting edges. You get your cutter diameter. That one makes a lot of sense. And then sometimes we'll refer to reduced shank end mills. So if you look at these two end mills, they have the same reach. If I'm holding on to this, oh, that's weird. If I'm holding on to this portion of this one and this portion of this one, I can get to the same depth in a part, but there's less cutting flute over here than here. What would be the difference between those two? Who wants to chime in and talk about why we'd want to use a reduced shank versus a full flute? Any thoughts on that front?
On a reduce.
Oh, go ahead.
No, you go first.
If you're like cutting deep, but you don't need to cut constantly, like you don't need that full length as like the long one. So that way there's less rubbing. Maybe?
Yeah, rubbing is definitely, that's why the reduced neck exists, is to prevent rubbing. With this guy, if this portion of the flute is touching something, I don't know, would we call that rubbing, Austin, or would that just be kind of tickling the part? It wouldn't really cause rubbing, would it?
You're not rubbing, you'd just be recutting.
Cool.
It's kind of like a spring pass almost.
Yeah, that makes sense. Yeah, so Elizabeth, you're on the right track. The reduced shank prevents rubbing of a solid shank. If I had a tool with this long of a flute length in there and I'm using that whole flute length, great. If I'm using the last ½ inch of this tool, I might as well use this tool. And Austin will probably talk a little bit more about using, like what portion of the flutes you're using and what you're not. Okay, we also have a helix angle on spiral end mills. This helix angle is measured from that center line. So when you talk about a 45-degree helix angle versus a 30-degree helix angle, those helix angles have some properties and they change some things that we're not going to talk about right now, but we might get there eventually. Also, sometimes you'll get what's called variable helix end mills, and If you guys got a chance to watch that Haas chatter video, you got a little bit of a background for what a variable helix end mill does. Keeps those tuning forks from being on the exact same frequency in your part. Same thing with the pitch. So the pitch is the spacing between teeth. You'd think a 4 flute would just have 90-degree pitch, but we like to have variable pitch end mills as well. Space it just a little bit oddly so it breaks up those harmonics and stops chatter as well. All right, and that was kind of a rapid fire through terminology of end mills. Any questions on the terminology specifically? Awesome. All right, Austin, take it away. Take it away, Ern.
Yes, Harry Potter. Okay, so addendum, just that last thing. There's a few other things that come up when you're looking at your tool libraries. Obviously, there's completely different styles. You have bull nose, you have chamfer mills, you have ball nose. There's lots of different stuff. You have a lot of different tools available to you, but they all have that same vocabulary that Tyler just reviewed. Okay, let's see. Can I share yet? Yes, I can. Good. Hold this up. All right, can everyone see that? Is
I got
my
it.
screen being shared? Okay. Did anyone have a chance to look over this at all yet? Yes, some? Sweet.
I opened it.
That's good. The goal of this is going to be to get you to start thinking about some of the many principles behind feeds and speeds and what sort of variables affect your feeds and speeds. We're going to go through this document and talk about some of the different things. I'll give some recommendations, but up front, I want you to know a couple things. One, these are my opinions. They're not necessarily correct because there are so many ways to skin this cat. For example, Tyler talked about harmonics. If you are getting harmonics, you can move your spindle speed up or down and possibly avoid that harmonic. So there's not one right way. But I still want everyone who's running a CNC machine or even a manual machine to be thinking about these different principles and how they can affect your feeds and speeds. So to start out, I'm gonna look at my notes here. Oh, I just want to throw one thing up before we dive into this. In my digging around the tutorials for Fusion, I did find some really awesome tutorials that are specific for people transitioning from Mastercam to FusionCam. So for those people who are familiar with Mastercam, there's some really good, quick cut to the chase videos for that. All right, but let's go ahead and dive in. I'm gonna send us to some breakout rooms. And in your breakout rooms, I want you guys to talk about 3 different things. First, what are some of the principles on this sheet that you hadn't considered before and how they affect your feeds and speeds? Are there any principles that you were confused about? Like, I'm not sure what this means or why would that affect my feeds and speeds? And then after that, just generally discuss the different things you learned. So Tyler, if you could send us out, that'd be awesome.
Gotcha. Austin, you want 3 people per room or 2 people per room?
3 is probably good.
Okay, great. Beautiful. And I will hop in the room that you're not in, Austin.
Perfect.
And I will send out a message to everybody.
if you are, I can't see it.
What was that?
Are you sharing your screen? Because if I don't,
No, I'm not. I was just looking at the.
okay.
I could share my screen, I guess. Let's see.
Kind of hard to see when you share it. So I just put it up on mine, but
Is that? Does that look right?
Yeah, I can see it fine.
Okay. Cool. How do I? Oh, that's that button. Okay. So we're supposed to be talking about some of these, looking at these different parameters that you can vary and see what things are new to us. So first thing is, let's see, we got tool stick out.
Oh, hello, Tyler.
Hello.
I was just about to pull up a chat thing with you.
I'm just lurking. Don't worry.
Okay, sounds good. If you want to leave us in here for like a few more minutes, 2 or 3, we're probably good. So something that I thought was kind of interesting that I didn't think about when I was starting feeds and speeds was this last one is chip size versus pocket size. What this principle alludes to is chip evacuation. If I have, say that really long tool that Tyler had showed, that had flutes going all the way up the tool. If I take that tool and side cut on the outside of a block like this, and I just side cut until I make just a peg in the middle, you can go to town because those chips, even if they were 3 inches long, they'll fall off the part.
We have here
Use the whiteboard feature. Draw.
an end mill of sorts. And you can see this one's got 2 flutes on it. I don't know how easy that is to see. So if when you're cutting, if you're going at a certain speed, then it's going to be moving in a certain direction at the same time that it's spinning. And so chip load is how far it moves from when one tooth cuts to the next. Does that make sense?
Yeah.
And that translates directly into the thickness of the chip that you're shaving off. So that's one parameter that's, you know, regardless of your spindle speed, you generally want to keep the same. So
Here is an image that helps visualize that. If you
oh, hello, Tyler.
look at that. Can you guys see this hot tip of the day thing?
mm-hmm.
Yes, sir.
So you guys are going to watch this afterwards. So this is your feed per tooth. That end mill is moving this direction. And that's the chunk that each tooth bites off of. Another thing that's cool about this picture is it shows it's not a consistently wide wedge, which is an interesting concept. Great. Anyway.
Thank you, Tyler.
Welcome.
All right, so tool diameter. Okay, so why don't y'all tell, not you, Tyler, but everybody else, you two included.
All right.
What can you do if you have a larger tool diameter? And so you go from a 1/2 inch to a 1 inch. What do you do with your feeds and speeds?
Slow down.
Which?
Both.
You think so? I mean, that's definitely an option. Why would you want to slow it down? You're not wrong, necessarily.
Can I jump in real quick and just say, like it was talking about in the video, actually, no, you guys didn't watch the video. You'll watch it after. Feeds and speeds, you have to be careful when we're talking about RPM versus feed per tooth. So I think you're right. You definitely slow down your speed because you got a 3-inch end mill versus your 1/8 inch end mill. The 1/8 inch, you're going to run as fast as humanly possible. And that 3-inch, you're going to be scared to death of running that thing anything larger than like countable RPMs, you know? So yeah. So when we're just discussing this, make sure to talk about whether you're talking about feed or speed. So how fast the tool is moving versus how fast it's spinning.
Yeah, and another thing to watch out for is when you say speed, you can either be talking about spindle speed or surface feet per minute. As a general rule, I tend to prefer talking about things in terms of chip load and surface feet rather than than
Flute's life or the tool's life depends a little more on just how you're using it, if the flutes are wearing out or not. Although it's way easier to break the one without the solid core going up.
Yeah.
How's it going in the other room, Tyler?
I was just messaging you. Discussion's going great there. There are only a couple items in as well.
Okay.
So it's not unproductive.
So Austin, quick
Okay.
question regarding.
I'll just let you make a.
So my question is, as far as like chip size is concerned, you want to have smaller chips. I mean, like, because when we're like turning things on the lathes, you want to have like a healthy chip, right? Like you don't want it to be just like grinding into little pieces of dust. But when you're CNCing something, do you like what's the general rule? Like, because obviously you don't want it to bird's nest. But like what is your thought? What is your thought on that?
Yeah, there's a bunch of different things that go into it. You don't want to break the tool. Okay.
Number one priority.
Seems super stupid, but that's where you start. You go, okay, I don't want to break this tool. And then you move to how can I extend the life of the tool? You're going to extend the life of the tool actually if you have really long chips, meaning a small step over and a tall step down. What that does is it doesn't wear out the tips of the cutter. The tips are always the first thing to die. They're the most fine. They're the weakest part, and they are literally always used no matter what type of cut you do, with one caveat. So because of that, you want to wear out the other parts of the tool similarly to the tip. So if you use the full flute, great. Now in the case of
end mills, using surface feet is really useful because then you can use the same surface feet for any diameter tool, and that'll give you the same finish, ideally. It'll have a faster spindle speed for higher RPMs, for smaller end mills, but the surface feet will be the same. And in case you're wondering, the way to calculate that is you have to convert revolutions per minute to linear feet per minute by, let's see, revolutions per minute. So you divide by 60. Oh wait, no, you don't have to do that because we're not doing seconds. And then you, let's see, one revolution. That's so you divide by the circumference, not diameter, but the circumference in feet, and that gets you your surface feet.
The what divided by the circumference?
So you take your tool and you have a certain surface feet that you're shooting for, right? A target surface feet. So let's say you want to have your cutter spinning at whatever speed necessary to attain 1,000 surface feet per minute. What you do is you take that surface feet and you divide that by the circumference of your tool in feet. Conversely, you can also just plug it into whatever calculator Mastercam or Fusion 360 has, and it'll just figure it out for you, which is wonderful.
Okay, guys, I think Austin's calling us back in about a minute. So go ahead and take a minute to wrap up discussion and then hop back to the main session. Welcome back, everybody. Welcome back.
Oh, we all just teleported. That was cool.
All right.
Alrighty. Let's see. I'm going to pull this back up. Well, no, before might be good to look at. Okay. This button. Let's click on this. And then this. Is that really small on your screen, Tyler?
The free kind of talking about just now.
Yes, you are muted, Tyler.
I'm on a really big screen and it's small for me. It looks like it's showing just the window on half of your screen.
Okay, let's fix that. Better?
No. Give me 3, 2, 1. No. For some reason. Oh, there it goes. That's easier to see for me. Is everyone else easier too?
It's better for me too.
Okay,
Great.
sweet. All right, so we'll put up in the Slack channel another link after this lesson with some suggested answers that I put down. I already have that filled out. It's just a duplicate document on the lab drive. But I just want to talk through some of these things. What are some stuff that came up in your breakout groups that were interesting? Maybe let's start with some things that you hadn't thought of before affecting your speeds and speeds.
Well, we talked a lot about, I mean, for me, a lot of these things I haven't really thought about, but there's like the birds nesting is a really interesting thing to think about, and just the chip size and things like that.
Yeah. So long chips and deep pockets. What are some other ones that came up?
Long chips and deep pockets would be bad, right?
Very bad.
Okay.
So what happens in that case, we'll just talk about that one for a second, is that you have these super long chips that tangle really, really well. And then they have a hard time getting out of the pocket before the tool comes back around and cuts in that same location, and then they get pulled back into the cutter. It'll do a bunch of things, from like make your surface finish terrible to breaking the tool. So sometimes you gotta, if you don't fix the problem, you gotta like stop the machine, open the door, pull out the chips, start again. And it's super awful and annoying. There's other ways to fix it though.
Fun story. One of my first experiences watching CNC machining was Caleb being one of the first people to learn the VF4 back when it was in the motorsports lab in the Fletcher. And we'd hiked over there with a big bucket of tools, and Caleb successfully bird's nested a really long, fat end mill. And I distinctly remember the moment he was like, it'll be okay. And it went straight back down to that pocket and goes, whoosh, and just broke the tool.
Last words.
It'll
be fine.
I wasn't working at the shop
It'll
at the
be
time,
good.
so I was like, well, Caleb knows best. And Caleb didn't know best, so.
Yeah, knowing best is who's made the most mistakes.
That's cool.
Okay. Let's see. Tyler, our goal is to be about an hour, right?
Yeah, somewhere in the 45 minutes to an hour range. And I have router stuff to chat about briefly that I can spend 5 to 10 on.
Well, I'll just, for ending, it sounded like the discussion was really good in the breakout groups. I'm going to just breeze through these really quick and give a few thoughts on how these principles might affect your feeds and speeds. I would encourage you to go look at the suggested answer sheet after this class, review it, see what things you disagree with and why, and just to start thinking about these principles when you're machining. First off, before I go through them, it came up in our breakout group, why would you make certain decisions? You have to start out with the dumbest question of, what do I care about? Is it, do I not want to break my tool? And then how do these affect that? Or do I care more about the surface finish and how do these affect that? That'll change these answers. So tool stick out to start. Obviously, if you stick your tool out more, it bounces around more. So you can't be as aggressive with your feeds and speeds. You need lower tool pressures, which means higher speeds and lower feeds. Or you lower both to keep the ratio similar. Tool diameter, This has to do with the Haas video. And was there a question?
Flies through your shirt.
Does it really?
I don't know.
Okay, sorry.
Oh, never mind. Not a question.
Gotta get like a cloud.
The tool diameter has to do with your linear cutting speed. Larger tools, you run at a slower spindle speed, and small tools, you run at a fast spindle speed. Flute count, this one's a little subjective because with more flutes, you can go faster, but with less flutes, you have more room in the gullets for larger chips. So it's kind of a trade-off between that. 3 flutes usually ends up pretty good for soft material. Tool material, obviously carbides you can run more aggressively. Stock material, more aggressive in soft material. Tool coatings, this is kind of an interesting one. Tool coatings are not useful until you run really hot and aggressive. So if you're using coolant, you're not getting anything out of the tool coating. But if you run dry and hot, so an aggressive cut will get hot, then the coating becomes useful. It starts to help the chips come off the part and the tool better. It has to do with lubricity. Coolant and lubrication, super useful. It does what coatings do, but in addition, it actually sprays the chips out of your cut, which is super helpful. So you can be more aggressive with flood coolant. Long reach. You have to slow things down with long reach. We already talked about this. But if you have a reduced shank versus a long reach with a full flute, like Tyler showed in that on that webpage, the reduced shank is solid down to just where you need the cut. That is much more sturdy than having flutes the whole way, which removes the core material. So it deflects less. You can be more aggressive with reduced shanks. And the other added benefit is it shortens your chip size. And so you don't get bird nesting as bad with the reduced shanks. Step over and step down. These are very integral. It just has to do with how much material we're moving. If you step down a bunch, you should not be stepping over a bunch. But if you have to use the full cutting diameter, you have to step down a small amount. Hard internal corners, I just want to spend half a second longer on this one because this is what was mentioned in that Haas video. You guys remember the constant engagement? From that video, he put up an adaptive or dynamic tool path. If you can get constant engagement, you can get more aggressive. But if you have what are hard internal corners where the tool goes and makes a 90-degree or a 45-degree hard corner, in that corner, the tool is seeing a lot more material to cut, and you have to slow your entire tool path down to accommodate for not breaking in that corner. So avoid these at all costs, but sometimes you can't. Stock rigidity.
Can I say something on that?
Yeah, go ahead.
Hopefully this won't matter as much for the shop saber, but at least, if you ever have to do something on the shop bot, hopefully you never do. But if you do, one thing about adaptive tool paths is there's usually a lot more curves and stuff in them, which on some machines, it slows things down. Hopefully you never have to worry about that, but it's something to consider.
Yeah, for those that are on the shop bot, it does straight lines great. It is terrible at lots of curves.
That's why we're getting rid of it. That's why we're getting rid of it, because it sucks.
Yep, I totally agree. But to Luke's comment, it's actually something you really want to think about. What do I care about most? And in the case of the shop bot, I don't want to sit there for literally 8 hours while I do one pocket. So I'm going to abuse the tool a little more and get out of there 7 hours quicker. So the last one, stock rigidity, stock stick out. This just has to do with how solid your stock is. If it's not solid, if it can bounce around, you got to back things off. Tool tip geometry. The only one I want to highlight is between these two. With a square nose versus a bull nose, the square nose has a sharp point that breaks easy and it's always being used. So with bull nose, you can run them a lot more aggressively. That's why we've changed some of our tools to bull nose. Entry motion, straight plunge, you have to back everything way off. We already talked about these. You saw resonant frequency, so I won't talk about that too much. It was in the video. So those are just some things to think about. It's not a comprehensive list, but when you're camming, you should have these types of things in your mind. And how does my specific situation affect the numbers I'm about to put in for my feed and speed. And what do I care about the most? So with that, we'll pass it back to you, Tyler, for some router adjustments.
Yeah. Austin, leave your screen sharing up. I can
We'll do.
Annotate. Which, if you guys ever want to make marks, you can go to the top of your screen and it says you are viewing Austin Johnson's screen. You can hit view options and hit annotate, and then it brings up a little pencil and you can make, I'm writing in white apparently. Let me change my color real quick. There. You can make annotations. You can be like, hey, Austin, what does this mean? And then you can come in and clear that later. So if you ever, it's a helpful thing for any of your classes. Okay, get rid of, why are you being weird? Okay. So yeah, just a quick addendum about router world. There's a couple things that change. The biggest one is the fact that all of a sudden, we're not working as much with blocks of stock as we are with plates. And if you've ever dealt with plate stock on the Haas machines either, plate stock is a whole different ball game. Nothing is ever fixtured well, just period. That's what happens. We're gonna be lucky enough with the Shop Saber that we'll have a vacuum table. But when you don't have a vacuum table, another consideration of your hold down method is, I have a plate and I've screwed it down in 4 corners. That means the middle is liable to pop up and down and chatter vertically. So then things like a spiral flute end mill, which pulls up on material, is a bad idea. You use a straight flute end mill, which will push it off to the side, or use a down cut, which will shove it down into the table. That helps a lot. With routers, we also tend to take a little bit different of a strategy. With a VMC, like the Haas machines, you tend to want to use as much of the flute length as you can, except in cases like a deep pocket where you don't want long chips. You tend to use as much of the flute length as you can and just feed slower. Routers tend to be less rigid, and things tend to be a little more shaky on the tip. So routers tend to do shallow depth of cut and feed really fast. For reference, when Alex Laraway was doing aluminum on the ShopBot, he was doing 40 thou depth of cut, but feeding at 200 inches per minute. So you tickle it and you cook fast. Because of that, part of it is because of the rigidity, and part of it is because routers are really susceptible to keeping chips down in pockets that you're cutting, because you tend to be cutting directly into a material. So slotting, which you'll learn a little bit more about later. Yeah, tools are also different. You get a lot different shapes of tools, and you have to think about whether you're using spiral, down cut, straight cut, V-groove, things like that. And you don't have as much control over stick out. Yeah, routers are just a different ball game, and we'll talk about feeds and speeds in context specifically. But routers, there's also danger of burning things. When people cut wood a lot, if you've ever looked at the ShopBot's spoil board, you'll see lots of burning happens. On VMCs, there's not a ton of danger with going too slow. With a router in wood or in plastic, there's a lot of danger with going too slow. If your feed is too slow and your speed is too high, you'll burn things in wood and literally light fires. Or in plastic, you'll melt it into a puddle and you start throwing melted plastic all over the place. So we're looking for ways to teach a little bit more intuitively those feeds and speeds, but just keep those in your brain. Okay, guys. Thank you for all coming. What we're going to do is I'll send out our post-class assignment, but what it's going to be, I'll just tell you guys briefly. You're going to model or import something into Fusion, and you're going to go to the manufacturing tab, and you're going to put a few tools in your tool library. So play around inside there. Just look at what those samples are. We'll send out those. We might wait a little bit on sending you guys the VF4 and DM1 libraries for Fusion, just because we have to get them back in order. You're going to watch a Haas tip of the day about feeds and speeds. And then pre-class for next time, you're going to go back to that same Fusion tutorial that you guys did one lesson of, and you're going to do the rest of those lessons. That will get you a brief intro, just like a 4 or 5 minute video for each type of CAM toolpath. And then we'll spend a lesson on each type. Okay, guys, any questions before we go?
Tyler, I've got one for you.
Yeah, go for it.
For the subsequent trainings, we're going to be focusing primarily on router applications, correct? Or do you want to somewhere in between?
That's open for debate.
Okay.
Because I know for those of you who are more familiar with VMCs, it might be better to take a router-focused approach so you get more of that. We also have several people here who have not done much on the Haas machines. Maybe we'll do a poll next time or something on that.
Okay. You and I can chat offline.
Yeah, good point.
It may be better to send out a library of a couple tools so that everyone has. I know that a lot of the people in this video don't have a sense for what tools they may want to use. So if it's router or mill, it doesn't really matter. But if we send out like 5 tools and say, hey, mess with this library.
Great, that sounds awesome. All right, guys, thank you so much. Keep learning and have a good one.